works here as a scientist 6, and has been a long part of AAP for a long time, so many of you know him quite well and don't need an introduction probably, but many here also don't know him. Larry Corman works in a variety of fields, turbulence being the central theme to a lot of them. He also does a lot of applications of his theoretical work in turbulence for aircraft and other applications. Is well known for his warning system to help pilots avoid turbulence, which led to an award from NASA and a 2003 listing of 50 outstanding achievements of the year in Scientific American. I was doing a little bit of background research on Larry and found this really interesting article from David Hosansky, who's one of our esteemed writers here at NCAR. And going way back, Larry spent time in 2 Zen monasteries along the California coast following high school, and immersed himself in a lot of different subject areas, including Russian literature, which I contend this eventually contributed to ways to help airline pilots avoid the outcome of climate and punishment. And then, after that, he began taking classes in community college, and this is where he developed his love for science, and including the field of physics. So he did get his bachelor's degree in science in mathematics and physics at the University of California, Santa Cruz. And then came here to Boulder to work at UC Boulder towards his master's and PhD in physics. And during this time, he started working part-time as a computer programmer, but eventually came here to work full-time as a scientist, starting out in the field of microbursts, which is one of RAL's legacies, and then moved on to more general turbulence problems, signal processing, and a software system called NCAR, Efficient Spectral Processing Algorithm, known as NESPA, which helps pilots navigate around storms to avoid major turbulence. Larry provided this quote by David Hosansky provided this quote by Larry that I think is a good inspiration for our work when we're hitting roadblocks. And Larry's quoted as saying, "To me, it is a matter of creativity. You also have to realize that not all of your ideas will be good ones. You have to keep trying so that eventually you will find the one idea that does work." And obviously Larry has found more than one idea that works in his research legacy. So I'll turn it over to Larry to talk more about his research.
Thanks, Chris. As you can see, I have a co-author here, Kent Goodrich, who unfortunately is unable to be here today. So hopefully he'll be able to see this online. So Kent, this is solid collaborative work that he and I have worked on for many years, on and off, in the midst of all the other projects we've had. So this work is pretty technical, and I worked really hard to make the talk less technical. It's not non-technical, but it's less than it would be, say, if I published this in a paper. But given that, since we have a small group here, please feel free to interrupt me, because I do that all the time to other speakers. If you have questions, if I use jargon or terminology you don't understand, really feel free to jump in and ask a question, because it's better for you to understand what I'm talking about as opposed to it going over your head, and then you lose the train of thought as we go forward. Okay, so let's start off with some real basic definition of energy dissipation rate. Where does it come from? Well, we all know of Navier-Stokes equations, and you can take the Navier-Stokes equations and do a statistical analysis of them to look at the fluctuation of the velocity field and also temperature and other constituents. And you get a formula here that, get this out of my way. Okay. The formula very symbolically here describes how the energy changes in time, the turbulent kinetic energy changes in time based on transfer through the fluid from different sources and forces, and production due to external forces and sometimes internal forces in a volume of fluid, and also the dissipation, how the energy is leaving the system, typically here via viscous forces and turning into heat at very small scales. Now, the energy dissipation rate, by definition, through this equation is, it's a combination of lots of spatial derivatives. So I'm not going to go into that part because it's not really useful, because that requires, derivative calculations. And in the real world, we never can do that because we don't have infinitesimally small displacements that we can make measurements on. We have small ones, and so we can approximate those, and often those are very good approximations for the scales we're interested in. But practical calculations typically rely on this theory of Kolmogorov that first came out in 1941. And the idea was for isotropic flow, for high Reynolds flow, there is a range of spatial scales where the external forcing and the internal dissipation are not affecting that fluid volume. So in those scales, he postulated, and we've found from empirical evidence over many, many years, that the only parameter that is determinate there is the energy dissipation rate. That's amazing. And it's also very useful, because if you have these spatial scales where you only have this one parameter that dominates it, you can solve for that parameter. You don't have to look at large numbers of other parameters and lots of derivatives, all these external calculations that make difficulties here. So that's a beautiful theory. And we found that this theory works well beyond the scales that it's typically assigned to, beyond the inertial subrange. Or, well, how do you mean inertial subrange? It's really an ambiguous definition. It really means far enough away from forcing mechanisms and far enough away from dissipation, but you're never really there. And so it's an ambiguous term. All right, so the other thing he did was use dimensional analysis. Remember, Kolmogorov was not a physicist or a turbulence person. He was a mathematician. And if you look in the mathematics literature, he's well known for a lot of things in mathematics. We, in turbulence, know him from what he did here, not what he did in mathematics. So brilliant fellow, did a lot of great work. So what he came up with was this inertial subrange theory that says that the structure function, which is basically you take velocities, components of velocities at a certain displacement from each other, and you look at velocities either parallel or perpendicular to that displacement, and you take the difference of those, you square them and average them. And this is what I'm calling a second order structure function. There are many other orders that you can look at. So when I use structure function in the context going on, it's really the second order that I'm talking about. Okay, there are other orders. So what this says is within this inertial subrange, you have this very simple formula that says that the structure function at a given spatial lag, rho, is given by a constant times epsilon to the 2/3 times that displacement to the 2/3. So you know the displacement, you assume the constant, you can solve for epsilon to the 2/3. Simple. What could be more simple, huh? Okay. But that is not the whole story. Before I get to the other parts of the story, which is the main part of this talk, there's another approach that you can take in the wave number space, Fourier space. So wave number here is, you can think of it as inversely proportional to a wavelength. It's a wave number, it's radians per meter. Now, turns out Kolmogorov did not come up with these equations, even though he's known for the 5/3 law. Everyone thinks 5/3 law of Kolmogorov. He didn't do this. It's unclear who actually did it. He was either Obakov or Onsager, who was a physical chemist, actually had Nobel Prize in chemistry, who came up with this wave number version of this and the cascade through wave number in the inertial subrange. But anyways, it's another simple, relatively simple formula. Again, epsilon to the 2/3 is the primary parameter, and here k to the 5/3, so it's inverse proportional to a known wavelength. And again, you can solve for epsilon in these cases. That's really nice. Now, why is epsilon a useful parameter for us in atmospheric science? Well, these inertial subrange scales, as I mentioned, it's kind of ambiguous, but it's on the order of centimeters to tens of meters to hundreds of meters, depending on, if you're in the boundary layer, if you're in the free atmosphere, what's causing the turbulence. But those are just general scales that you can think of. Well, those are scales that we live within, right? Meter scales. And aircraft fly through meter scales, and anemometers measure, centimeter scales and meter scales. So these are practical scales which makes epsilon a useful parameter for us to describe the turbulence in the atmosphere. So not only do we have this theory that is very simple, that we have only this one parameter that's needed in this inertial subrange, but it's also useful for us. It's not light year scales, and it's not, angstrom scales. It's physical scales that we deal with. Okay. All right, so talk a little bit about spatial versus temporal. So in turbulence, you have temporal variations in the fluid, and you have spatial variations in the fluid. What I'm going to be focusing on here is spatial variations in the fluid, but typically we go out and make measurements in time. So we have an aircraft flying through the atmosphere. So it's measuring in time, but it's really measuring what's happening in space. And the same with, say, an anemometer. The fluid is advecting by the anemometer, so it's really a spatial field that we're looking at, but we measure as a function of time. So there's this hypothesis due to Taylor back in the 20s, who says if the advection speed is fast compared to how you're sampling it and the turbulence intensity, you can make this assumption that the field is not changing in time as it moves quickly by the sensor, or the sensor moves quickly through the fluid. So it's very powerful. Now we can go in the time domain, and we have all this wonderful signal processing methodology in the time domain that we can apply to these problems. So that's kind of where the rest of the talk's going to fit. So when you think time series analysis, that I say it's really the spatial field that we're after. It's not the temporal evolution of the turbulence that we're talking about. Okay, so let's start in the real focus of the talk. If you look in the literature, almost all the theoretical descriptions of turbulence are based on assumptions that are not explicit. And those assumptions are that we can use Fourier analysis or correlation analysis that assumes a continuous velocity field, which is probably reasonable until you get to quantum mechanics. It's a reasonable assumption that the fluid is a continuum. It's not discrete. But our measurements are discrete. So because we can't measure things at infinitesimal scales, which the mathematics tells us we have to, we measure things at delta t of 10 hertz, 8 hertz, 1 hertz, whatever it is. It's a discrete sampling that we have. And furthermore, we make measurements over a certain time window. We don't put an anemometer out there and say, I'm going to make measurements for infinite time, because that would fill up your disk space pretty fast, right? Or we'd all be gone. The sun would blow up by the time we actually got there. So we have to make measurements over a finite window. And also, we hope that over that window, the intensity of the turbulence hasn't changed such that we're making measurements of different processes going on. So we assume some level of stationarity, local stationary. By local here, I mean in time. Okay, so how do we quantify this mathematically and characterize this? So what we do is we assume that we are measuring at discrete samples, k delta t, and that our velocity field u, or it could be temperature, although most of my talk is going to be, or not most of the talk, all the talk will be about velocity fields. But a lot of the theory applies perfectly well to temperature fields or other scalar fields, non-active scalar fields. So what we do is we have our velocity field u, we hit it with a weighting function. Now the simplest weighting function is shown here on the left, rectangle window. So we just start measuring, we stop measuring. No weights, or all the weights are 1. That's a rectangle window. Now, actually, when you do any calculation, if you don't stick a real window in there, you're still putting a rectangle window in there, and you have to take that into account. And I'll explain how that comes about later. Another window is this Hahn window. It's kind of a cosine squared window. There's a whole, theory in signal processing literature about windows. Best window for this, best window for that. They're all pretty similar, so we're not going to get into details of windows here. But the key is that these windows have a strong effect, both in the time domain, which is surprising, but also mainly in the spectral domain. And over on the right, I'm showing the power spectrum of these two windows. So the black is that's the rectangle window, and the red is the Hahn window in this case. So you can see large difference at large frequency. And that's one of the reasons for these windows that aren't rectangular, because this discontinuity at the end creates a lot of issues at high frequency. It's not surprising. And so the Hahn window smooths it out, and so you get a faster decay, so you get less effect at high frequencies. But it's hard to see, but the trade-off you get is now that this window is wider, the Hahn window. It's better at high frequencies, but it's wider at low frequencies. And what happens, and I'll explain in a little bit, is that these windows get convolved with your data, of the spectrum of your data. And so one of the problems with these windows is they create correlation between the spectral bin, because you're convolving these curves, essentially, with your true spectra. And you can't unconvolve them is the problem. Okay, so sorry for some equations, but we'll see if we can get through them without, yeah.
So why doesn't the Hahn spectrum approach 1?
Very good question. See, I knew I brought you here for a reason. All these windows, as the length of your interval goes to infinity, they all go to delta functions. And that goes back to what I said very early. So when we talked about continuous infinite window, when you go to infinite window, all your wonderful characteristics occur. But the whole point of this talk is, what do you do when you're not in that regime? And especially if you're like looking at 64 points or even 32 points, a very small window compared to infinity, right? So you have to deal with these effects. And so that's the whole key of this talk, is dealing with these effects, taking them into account in energy dissipation rate estimates. Okay, so beautiful theorem in mathematics called the Poisson sum formula. And I'm always shocked that in the signal processing literature, it's not brought out more. They kind of do it, they use it, but they don't mention it and the mathematics of it. And it's a beautiful theorem. What it says is that if I sample data, so first I'm going to sample. I'm not going to talk about the window length yet. So I sample data. So you build what's called a periodic summation of the spectrum, or whatever. This is really not spectrum and correlation. It's really Fourier and time. So it could be any two functions where you have the Fourier transform and the time function. So here it's correlations and power spectrum, because those are Fourier transform pairs, but in general it's any two functions. So you build up this periodic sum. So what do we know about periodic functions? Well, we can expand them in Fourier series, assuming certain mathematical conditions that allow us to do that. So you do that, and you say, what are the coefficients of my Fourier series? Well, it turns out to be, in this case, the correlation function, samples of it. So this function, Poisson summation formula, tells us precisely how that works. So, and then furthermore, the window function, the correlation of the window function, by definition, goes to 0 at m and minus m. And so you can now do a finite summation, and I write it this specific way because this is a DFT. So now you can apply all the nice properties of fast Fourier transforms and DFTs to this problem. So it says that I take the product of the correlation of my data, correlation function of my window, I take its DFT, and that gives this periodic summation of the power spectrum. Well, it's a problem, because when we do power spectra, that's what we get. We don't get the original power spectrum we wanted, we get this periodic summation of it. And you can't unwrap it. And then the second formula, a little more complicated, but what it says also that you can write this as a discrete convolution of the spectrum of these window and the data. So that's where the convolution comes in that I described earlier. So in the correlation domain, we get a product of these, the correlation of the data in the window, and in the spectral domain, we get a convolution. And it's that convolution that causes trouble in the spectral domain, because it ends up smearing things out. And it creates correlation between the values because of that convolution. It's not a delta function, it's spread out. And so it creates correlation at different frequencies. We'll get to that later. And then in the time domain, you don't have that convolution, but you have this product of the two windows. So you have to take those into account. But R sub W here is a known quantity. You know, you either use a rectangle, use Hahn, use some other window. So that's a known thing. And let's say you assume something about the correlation of your data, like a model. Well, you can do this calculation here very simply, and that tells you what your output's going to be. Okay. And so here's kind of a quick side-by-side comparison of the infinite window continuous time version, which is the upper formula, and this correct form that we have to deal with in the real world. It's the Poisson sum formula. And so we deal with the second one, but all the theory is based on the first one. All right. I think I've mentioned all these other things. Well, the periodic summation, where that comes about is in the sampling. And so you think of it, you have these complex exponentials, and you have a discrete sampling in there. It means that you're going to get periodicity in it. And so that's what happens. So it's the Fourier transform. It's those complex exponentials that causes aliasing in the frequency domain. The time domain, you don't have that, but you still have this product of things. And so there's these two aspects that happen. All right, let's see. Oops, I went the wrong way. All right, so now, quick sidebar. How are we doing on time, by the way? Good? Okay. All right, so I use two m-point DFTs. And the reason for that is when you take that correlation function, even though it's for a univariate time series, like one velocity, it's symmetric around zero lag, okay? So the values at negative lags are equal to the positive lags, but there's still 2m of them, even though you started with m data points. And these complex exponentials then are periodic in 2m, okay? And so you can get a 2m point DFT pair with the correlations in the spectrum. So you can go back and forth between them. And this first formula here is a beautiful formula. It's not well known, but what it says is you go out, you take your data, apply a window to it, compute its power spectrum, and if I take its inverse DFT here, I can get the true samples of the correlation function. True samples, not artifacts. Well, it's sub V there, so it has that window function in there. But we know the window function. So technically, you can get samples of the true correlation function from all this damage you did to the data with windows and convolutions and aliasing, all that stuff. So it's a beautiful formula. If you use m-point DFTs, which actually most people do, you end up with this other formula, which is kind of it's an aliasing, in a sense, between the true correlation function and this other term that has some periodicity in it. Now, typically, if M is really large compared to A, that second term's small, and so you get what you're after. But again, the whole concept of what I'm trying to do here is talk about cases where M isn't really large, and you have that problem there. You can't get rid of that second term. But we don't have that with the 2M point. It's because those complex exponentials are periodic in 2M. Okay. All right, so now let's move back to structure functions. So if you have a stationary time series, and it's important to realize stationarity. Some people think that structure functions are somehow these magic things, and they are when you have other types of processes that we don't typically deal with in turbulence theories. So for example, if a Brownian motion, where you can't compute derivatives of the data. It's not stationary. You can't compute. Structure functions can still be defined in that way, and that's where Kolmogorov came into it, because he was considering those as a more general process as opposed to what we think of as in turbulence. But anyways, so the rest of the talk, we're gonna think of stationarity. So this relationship between the structure function, which I'm defining as D term, and related to the correlation function. So if you've been around turbulence for a while, that's not unusual formula, you've seen that before. The other formula tells you something about what happens, the relationship in the spectral domain. Now, I'm not gonna write out the formulas because they're a little more complicated, but with the discrete scenarios that I've been discussing, there's a beautiful invertible relationship between the structure function and the spectrum. So I'm using D again just as a generic structure function. Phi is the generic power spectrum. A is some matrix. Now, the matrix in this case is proportional to sine squared, so it's not that complicated, but it's a matrix of sine squareds for different discrete lags and discrete frequencies. And there's 4 delta F in there too. And then B is another term that's known and fairly straightforward. But you can invert this relationship. So now what I want to say with this is that everything you can do with structure functions, you can do with spectrum, and vice versa. So as we go through, we're going to see this old adage of use the right tool for the problem. And we'll see where these come in as kind of telling us what the right tool is to use, because we can go back and forth. You want to use structure functions? Please do. But I can get a spectrum out of that, or I can determine structure functions from spectrum, vice versa. So there's this beautiful invertible relationship there, and we're going to actually use that later. Okay, another sidebar on simulation. So our old colleague, Rod Freilich, which many of you remember, worked with us. We developed this simulation capability, which essentially says, give me a correlation function, a known analytic correlation function, and I'll show you how to simulate data that will produce, on average, accurate samples of that correlation function. And it does. It's a great algorithm. We use it all the time for simulation. So here's just an example here. This is a von Karman model, which some of you in turbulence or aeronautics might know of, others don't, but don't worry. It's just a model for turbulence that's analytic and has Fourier transforms, so it has nice properties. We can use it. All right, so here's just showing in black the theoretical spectrum from that Poisson sum formula I showed before, because I knew R, and from the data, I knew R from the window. I can do that DFT calculation analytically, and I get the black curve. And then I go off and simulate, average a whole bunch of those spectra, I get the red points. Pretty good. Same with the structure function over on the right. So this basically says we have a tool now for simulation that we believe in. It's accurate, it will produce correct spectrum, including the artifacts. You can see that tail at the high frequencies, that's the aliasing. I'll show you in a bit what happens at lower frequencies with the spectral leakage problem, and also you get the correct structure functions. So we trust this. All right, so here's an example a little hard to see. So let's start off on the top left. So the black curve is kind of what we showed in the previous plot, except now we're looking at different m values. Um, most people use n. I use m because I use Mathematica, and n means take a number, you have 1 and you take number, it goes 1.0. So Don knows this because he used Mathematica. So I use m instead of m, but it's just the number of samples, all right? So black curve on the upper left is the power spectrum you get with the aliasing and the spectral broadening. The green curve is the minus 5/3 curve. And the red curve is the spectrum you would get without the window effect, okay? So you can see in that case, the black curve is very different than the other curves. Now, as we move over to the right, we see they start getting equal to each other. So again, this is the whole small number of samples, m versus large. When we go to m, large, all things look great. You can use the theory with more confidence. But if you're stuck with small m, you better be careful because the black curve does not look like those other curves. And the same with the structure function down below. Here again, you don't have aliasing, but you still have the window effect there. So you can see for small m, the red curve and the black curve are quite different. And here it's just that rectangle window. That's the only difference. So it shows up pretty strong. But as we go to large m, it goes away. We're good. All right? But the whole point of my talk is, when we live in small m world, for some reason we're doing something there because we maybe don't have high rate sampling, or we're stuck with turbulence that's varying very rapidly and we don't want to use a long window of data, we're stuck toward the smaller m. Okay, so we saw these equations before. So now we're getting to the purpose of the talk, which is energy dissipation rate. So all before is preamble. Now we can actually get into the meat of the talk. And how are we doing time-wise?
20 minutes.
Okay, so we'll speed up. All right, so most of the time people use these formulas, which, as I keep saying, they're designed from theory based on continuous sampling and infinite windows. There's no effect of aliasing in spectra. There's no effect of windows in the correlation domain or structure function domain. And also there's no effect of windows in the spectrum. So people use these formulas as is and say, I'm going to estimate energy dissipation rate from them. So let's see what happens when we do that. So two kind of general classes of estimators. Least squares. So you come up with a model. So for example, we say, oh yeah, structure function theoretically is tau to the 2/3. So that's my model, and I'm gonna fit my data to it. So maybe I go into log space, make it linear, do a line fit. So that's a kind of a least squares method. So you can do least squares with weighting or non-weighting. Weighting typically is using either the variance of the data at each sample or a covariance, which takes into account the correlation between lags or spectral bins. And that latter one is called generalized least squares. All right, and maximum likelihood, which is kind of, I don't want to call it a gold standard, but it's a very powerful method. But it requires you to know either theoretical or empirical joint density function of your process. Joint, meaning I know everything at a given lag, say, and I know how it relates between all lags, and not just variances and covariances. It says I know all moments, infinite order moments. So it tells you everything about the process from the statistical perspective. All right, but maximum likelihood has these great properties in terms of these asymptotic properties which often work well even non-asymptotic regimes. So consistency, they converge to the true value, which is obviously something you want, and efficiency, which is a minimum variance, which is also something you want. So you have a estimator that gives you the right answer on average, and it has minimum variance, so the estimates don't jump around a lot. So that's the power of maximum likelihood. But as I said, it requires this knowledge of the PDF. Often you don't know that. So let's see, I think I mentioned this stuff already. So the other thing I would point out is again, in the literature, almost always, I would say 90% of the time, you see, oh, we're going to assume independence because, so you can take a joint PDF and by making the independence assumption, you say it's a product of the PDFs for each of your individual aspects. So for example, the PDF of the spectrum would be, I know the PDF at one frequency and another frequency. Independence means the joint PDF is just the product of those. So it makes it very simple. Is it correct? Maybe, sometimes, usually not. But it's done always, because otherwise, most of the time you can't get anything further out of the problem. You're stuck. Okay, so how about joint PDF with turbulence itself? Okay, so we're not talking about the PDF of, the spectra from velocities, but the PDF of the velocities themselves. We kind of want to know that. Well, unfortunately, most turbulence theory these days says, no, turbulence is not a Gaussian process. And mainly that comes from looking at very small scales. And at very small scales, you tend to get larger tails. And so, from a Gaussian process. So it's pretty clear it's not a Gaussian process. Now, on the other hand, for large scales, like in the energy producing scales, it does look pretty Gaussian. And in the inertial subrange, it's kind of sometimes yeah, sometimes not, depending on the scales. Okay, well, I'm going to assume for the scales that we're interested in here that it is joint Gaussian. Joint Gaussian is a very powerful and very strong assumption, though. So, but we're going to assume it here because otherwise my talk is over. So let's go forward. All right, so now let's look at power. The probability density function for the power spectrum, okay? So not the velocities. So I take the velocities. How do we compute a power spectrum? You take the Fourier transform, in our case, discrete. We probably put a window function in there. The real and imaginary part of that Fourier transform, we take the modulus square of those quantities, and we add them together. Well, it's the modulus squared. So we take the sum of the square of the real and the imaginary part, add them together, and that gives you the power spectrum. Okay, if you have a Gaussian process, you take a linear transformation of it, you get another Gaussian process. The DFT is a linear process. So if I take the DFT of a Gaussian process, power spectrum at each frequency is Gaussian. Well, not the power spectrum, but the Fourier transform. Then I take the sum of the squares of those. Now we assume that they're independent. And if I do that, then you get an exponential distribution. So that's the type of probability distribution you get at a given frequency, assuming independence. Is it really independent? No, but we're going to make that assumption. Well, we're going to test that assumption in a second and see what happens. All right, and for large sample size, it tends to be that way, okay? All right, so here's actually an example. And I'm going to go a little deep into this plot because there's a lot going on here. Doesn't look like it, but there is actually. So first of all, I have our simulation. I calculate power spectrum. So I take a little window of data, compute the power spectrum from my simulated velocities, and I do that over and over and over. It's like 200,000 realizations here. And then I build up I've picked two different frequencies, kind of a low and a high frequency, and I compute the PDF. Well, the black curve is the exponential density, pretty good fit. And the red one, that's what's really interesting here. That goes, see that formula up there? Remember I talked about how I can go back and forth between spectrum and structure function? Well, what I did was I said I take my data, instead of computing the power spectrum, I computed the structure function. And then I did this transformation up there and asked for what's the distribution of it. Lo and behold, it's exponential. So it basically says, if you gave me structure functions, I can produce the statistics of, the correct statistics of the spectrum from it. And I'm going to show you in a bit, I can do the other way, because I said I could. Better be able to show it. Okay, so unfortunately, structure function doesn't have a lot of those nice properties of the power spectrum. It's not the sum of the square of two Gaussian processes. It's the product of things. So structure function, remember we took differences of velocities, we squared them. So you end up getting squares of velocities. So what's the PDF of the square of a Gaussian thing? You know, good luck. Hardly ever you can find, you know, theoretical results that tell you, and usually they're very, very specific in the cases you can get. So taking products of stuff is a bad thing when you look at probability density functions. Not a good thing to do. But here we're doing it. So what do we do with it? Okay. All right. So again, we have that relationship between the structure function and the spectra. Well, the spectra had that nice, beautiful exponential. So why don't I use that? So I can tell you what the PDF, at least at a given lag, is from the PDF from this from the power spectrum, because it's a linear function there. And also, I point out that except for m going into infinity, neither the spectra or the structure function have closed-form joint PDFs. So that's a problem. All right, so here's the same plots now for structure function at 2 lags. So they're not exponential, they're kind of gamma-like. If you know gamma distributions, they're kind of gamma-like. And here, I don't have a theoretical formula for it. The exponential, I did. I knew how to do that. Here you don't, but at least I can approximate it pretty darn well. So the black curve comes from some beautiful methodology I found in the literature of basically taking PDFs that have kind of a gamma tail to them, and you can build up approximation by doing a method of moments. So you're matching moments of the data to moments of a expected PDF. And you do that, and you kind of get this polynomial adjusted gamma function. That's the black curve. And then the red curve is what I get from starting with the spectrum, remember those exponential, doing the coordinate transformation or linear transformation, and now you get those. So I don't have an analytic form for them, but I have a linear transformation that I can use. All right, we better speed up here. Okay, so remember I mentioned before these methods can use, the least squares methods can use the variance or the covariance. These plots are the covariance matrix of spectra in the upper and structure function in the lower. So by covariance, I mean you pick two frequencies and ask how they're correlated. And so that matrix there says, give me any ij pair and tell you how they're correlated. You can see they're close to diagonal. So diagonal would mean they're fully independent. So close to is about as good as we can get, but that's good. Structure function, not good at all. Highly correlated. And I will show you, so I'm not going to talk about that. So here's some examples from simulation. So, and I call this an unconscious bias. I really feel when I read the literature, people have this unconscious bias to use structure functions. And it's twofold. One, Kolmogorov. He said, structure functions, they're great, you know, so why not use them? So everyone wants to use structure functions. They use spectra, but they love structure functions. And also, structure functions that I showed from that previous plot, they're highly correlated between samples. And what happens is they look smoother. And if you see those kind of wavy structures, that's a telltale sign of correlated data. You often get that when you have correlated data, you get that wavy structure there. Oops, what happened? Okay, so you see that. And similarly, people look at spectra and go, that's so noisy, you know, it's gotta be bad. Well, there's no noise in this simulation. I didn't add any noise. that noise is coming from the independence between the frequencies. And so it's like white noise, well, exponential in this case. And so it looks noisy, and everyone goes, oh, spectra bad, structure function good. It's unconscious bias. But going back a couple slides, correlation structure, good for spectra, bad for structure function. Did I say structure function up there? The spectra. So it's just the opposite. So it's that high correlation that makes them look smooth, and people think structure functions must be better because they look smooth. All right, so now, in like 5 minutes, we'll talk about some of these algorithms. So 2 sets of algorithms. One was again, I mentioned maximum likelihood is really our powerful methodology, but it requires a lot. We have to have these joint PDFs. Now, I assume that we're going to use joint PDFs for the velocities. So if I have a time series of data, they're velocities, they're joint PDF, I'm assuming that. So you can compute a maximum likelihood estimate based on that joint Gaussian PDF. It's a fairly straightforward method. It's only really useful here in the simulation context, because in the real world, you don't know what that correlation structure is. And it doesn't allow us to restrict things to inertial subrange, because you've got m time data points. Where's the inertial subrange in there? I don't know. I don't have it. Now, we have what I call a pseudo maximum likelihood spectral method. So it says, in my spectra, I'm going to assume that covariance matrix is diagonal. Even though I know it's not, I'm going to assume it and see what I can get out of it. And you can build a maximum likelihood algorithm out of that. In fact, our NCAR in situ algorithm is that type of algorithm. And here we can restrict the frequencies to some range we think is inertial subrange. So that's a benefit. And it also, we can account for all those spectral artifacts that I talked about, aliasing and window functions. Okay, structure function algorithms. There's a pseudo maximum likelihood that I developed here, and it uses that formula I showed before, the relationship between the two. So it says, over in spectral land, I assume independence. So I have this joint PDF because it's the product of all those exponentials. And so that allows me to do my pseudo maximum likelihood in the spectral domain. Well, I can use the same algorithm over here with a coordinate change. So I say structure function of spectrum and vice versa. So I can do that type of algorithm over in the structure function domain. I don't know why you want to, but you can. And that shows you can. Least squares, this is kind of the common method people use. So they take a certain set of lags, they do a fit over it, or take a log and do a line fit over it. They don't do any weighting, and that's their estimate. Now remember, I said they're highly correlated, so not taking into account the covariance is a bad thing because they're highly correlated. And so that's the general least squares. So a couple comments here. All these methods, actually, you can compute them in the Fourier domain, spectral domain, because it's more efficient, actually. So computing correlation functions, you can do in the spectral domain. It's a lot more efficient numerically. Same answer, just different approach numerically. All the methods, besides the time domain one, I restrict either lags or frequencies to some sort of assumed range of inertial subrange. So we have the 2/3 law and the 5/3 law that we can use. And then all these methods accommodate all the artifacts. Okay, let's see, so here's some results. So these are like 100,000 realizations at each EDR level. Now, these EDRs are epsilon to the 1/3, not epsilon to the 2/3. So sorry about the change, but this is kind of a way we not typically, but sometimes we do it here. So just understand that for a second if you look at the magnitudes here. So going left to right, this is the power spectral method using that pseudo maximum likelihood. So I'm assuming diagonal covariance matrix. Next one is the structure function version of that. You can see they're very similar, as they should be. The next one is the standard least squares structure function. Pretty noisy. It's because it doesn't take into account the covariance between the lags. So you have, when you think of statistical independence and you take an estimate of something, you get like a 1/n scaling based on independence. When you don't have that, you don't get that property. So you expect the spectral methods for the same amount of data to work better because there's less correlation between the values. And then the last one is this generalized least squares. So it takes into account the full covariance matrix of the structure function. You notice it doesn't really it doesn't add much. And it's complicated to compute that. So why do it if you've got these other methods? And as I said before, here you have the spectral and the structure function method, about the same. Okay. Let's see. And then a new method. Okay, so remember earlier I said squaring those pesky Gaussian random variables is a bad thing because you don't get a density function you can make sense of. Okay, and I also mentioned that when we compute the power spectrum, we're taking the sum of the squares of the real and imaginary parts. Okay, well, what if I didn't take the squares? Because remember I said squaring is bad. So I don't take the squares, and I just compute the DFT, the discrete Fourier transform of the data. I have a real part and an imaginary part. Okay, remember I said that if you take a linear transformation of a Gaussian, you get a Gaussian? Okay, I didn't square, I did a linear transformation, they're still Gaussian. So now I have the real and imaginary part of the DFT, they're Gaussian. Okay, I've assumed they're joint Gaussian, so I can use all the power of maximum likelihood methods on those. Now, it doesn't come for free because I started with m data points, say. And now I have m real parts and m imaginary parts. Oops, 2m. It's not I have too many variables for the unknowns. So you have what's called a singular Gaussian. But you go look in the statistical processing literature, they know how to deal with that. So you basically look into a subspace where you have orthogonal eigenvectors and you span that space. Now it's not singular. It's a full rank system in a lower dimensional space. Now, how do you get there? Good luck. But there's a nice, beautiful method called SVD, which is singular value decomposition. And there's a numerical approach to that called a pseudo-inverse, because we need these inverse matrices when we do this. And it does all that work for you under the hood. Now, what you do have to do, though, is put a threshold in there. Because what it says is, I'm going to find the non-singular part of your matrix, but I have to have a threshold. Because you have these eigenvalues associated with those eigenvectors. And you want to pick, say, the biggest ones. So you can pick a set of big ones that match your, for some reason, how you think of the data. So that's how this works. So you have a parameter in there. So it's not free lunch here, but you can compute that parameter in a precise way, which I'll describe now, although how are we doing time-wise? Do I need to stop?
Start wrapping up.
I'll wrap up very quick because I just have a few more. So based on all the stuff I've showed before, and you're going to have to read the paper when we publish it, there's this theory of quadratic forms and Gaussian random variables. So it says for those maximum likely estimators, I can actually predict the statistical property of my estimators. And in this case, it turns out they're gamma distributed. And also, so that's what these are. These are gamma. These are the distribution now of epsilon to 2/3 for the different methods. And you can see they're all gamma. This is for one scenario, one energy dissipation rate value. And then you get this spread, the natural spread when you have a random process in estimating these parameters from these different methods. You can see the time domain is kind of the tightest of all of them. That's the best you can do. And since we've run out of time, I'll just throw out, it's a Kramer-Rao bound for those of you who know about Kramer-Rao bounds. So you can't do better than that. So it's the best. But these other ones are not that bad. They're pretty good. I didn't show the structure function one, with the just the standard least squares version. It's really wide. It's not good. So these are preferable methods. And this slide basically talks about these Kramer-RAL bounds. If you want to ask me after the talk, I can go through some of this, but it basically tells you how well, it allows you a statistical, precise statistical understanding of the quality of these estimators. Okay, summary. All right, so give a lot of information here. Sorry for the overload. I'm sure you guys are ready to get out of here. But we talked about some of the important things here. And specifically, I was trying to get this understanding of what happens when you can't use all these theoretical properties like independence and infinite time windows and all those things. So you have to deal with these properties. And we've shown how you can deal with them in a quantitative and precise fashion. So we looked at a bunch of different methodologies for computing energy dissipation rate, both least squares approaches, generalized least squares, and preferable maximum likelihood, and how those work. And we've shown that those have different characteristics and qualities. And this new method we came up with, which basically gets around a lot of the problems. I have never seen anyone in the literature do that algorithm. Maybe we'll find out if we publish it. Someone will say, well, Gauss did it, because that's usually what happens in mathematics. Someone says, oh, Gauss did it. So anyways, I think I'll leave it at that. And if you have any questions, feel free to jump in with questions.
All right, thank you. Great stuff. We have time for 1 or 2 questions. All right.
Thank you. This was very interesting.
Yeah.
You mentioned one of the tricks with the singular Gaussian PDF was having to decide how to do SVD and what eigenvalues to keep.
Yep.
You mentioned thresholding. Were you thresholding in a magnitude of the eigenvalue sense, or like I'm going to keep 80% of the energy?
Well, it's not the eigenvalues, it's the singular values.
Oh, sorry. Yeah.
Yeah, but so that was the slide I skipped over here. I actually explained how we do it. So what you can do is calculate this efficiency, which is the formula up there described. And so you can say, I want a 90% efficient algorithm. And then you can figure out, where to put that threshold in order to do that. It's not analytic. You kind of have to play with it. And all these things, use a different window function. You do this and that, different M. Everything changes. But there's an approach you can take to do that. So it gives you a quantitative approach to how to pick that threshold. We just picked one not at random, but one that kind of worked. But you can do it to actually choose a specific efficiency you want, which is a good approach, I think.
Thank you.
Thanks, Larry. Great, really interesting talk. I was wondering if you can go back to the slide a couple earlier showing the different PDFs of the eddy dissipation rate.
These?
Yeah, I was trying to wrap my brain around what we were actually seeing here.
All right, so you have simulated data and at one EDR level.
Okay, so you have a specific EDR there.
Yeah, these plots were over a range of EDRs. So now I'm just looking at one EDR level, and we're looking at the statistical variation. So basically, the vertical cross-section here. All right, so we picked EDR. The true value is probably close to the peak there. Yeah. And then, and so you get this natural variation. Even for, the quote truth, the best you can do, you still get a large variation there. That's turbulence, it's a random process.
Yeah.
So, question.
So I don't really see that much difference in the shapes of the distributions. Is there noticeable or?
I mean, because it's probably maybe the value I picked, So again, it's you pick a a vertical cross-section, it's that
So if you went further out,
you'd probably get more. And also, you see, these methods are fairly similar. And so, you know, except for that one structure function one, which I didn't plot there because. So let's see, the value I picked there is 0.5. So it's actually, or no, it's 0.3. So it's not that wide.
yeah.
And it doesn't really show the, you know, the real difference because like here, it should be a lot narrower, right? And these are all on the same scale, so I made them, you know, line up carefully so you could intercompare them. You know, that, yeah.
Thanks.
All right. Unfortunately, we've run out of time. It's unfortunately we couldn't invert this to spectral space, so we had more time. But let's thank you again for this great talk, and you feel free to talk to him afterward. Let's give him another round of applause.